All right, welcome to the deep dive. Today, we're going to try something a little bit different.
Okay.
We're going to focus on a single paper.
Okay.
And really do a deep dive on this one paper.
All right.
The paper is Attention is All You Need.
Okay, yeah, I've heard of this one.
Yeah, have you heard of this paper?
I have, yeah, it's very important.
It's super important. And, you know, for anyone who is sort of a beginner or an intermediate student in the AI space, and especially natural language processing, understanding this paper is pretty fundamental.
Oh, absolutely, yeah. This is a turning point.
Yeah. This is kind of where things changed.
It really is, yeah.
So the idea here is to give you a really solid understanding of this one paper and why it's so historically significant.
Yeah, and I think even today, if you look at a lot of the models that are coming out, a lot of them can be traced back to this paper.
Absolutely.
So if you can understand this one, you can understand a lot of what's happening today.
Yeah, and the central idea of this paper is this thing called the transformer. And as the name suggests, it really relies on these things called attention mechanisms. And the transformer kind of moves away from the ideas of recurrent neural networks and convolutional neural networks.
Right.
Which were really the dominant players at the time for things like language translation or just sort of understanding relationships between words.
Yeah, sequence modeling and processing, all of that was really ruled by these older architectures.
Yeah. So hopefully by the end of this, you'll kind of understand this paper and also just its historical significance. So to kind of give us a little bit of background, before the transformer came out, what was the state of the art? What were people using?
Yeah, so before this, really the kings of the castle were recurrent neural networks. These were the RNNs. You would see these architectures using LSTMs, long short-term memory units, or gated recurrent units. Those were really popular as well.
Okay.
And they were doing amazing things in the field, things like language modeling, where you're trying to predict the next word in a sentence.
Right.
Or machine translation, going from one language to another. But as powerful as they were, there were definitely some limitations.
Yeah, I would imagine, especially with longer sequences of text.
Yeah.
It seems like it would be pretty slow to process all that sequentially.
Yeah, that was one of the biggest issues with RNNs, this idea of parallelization.
Yeah.
Because they were inherently sequential, each step in the process depended on the one before. And that made it really hard to speed things up, especially when you're dealing with these really long sequences, like a paragraph or a whole document.
Yeah.
The memory limitations would also come into play because you could only handle so much data at once.
Right.
There were some clever workarounds, things like gradient priming to help the training process.
Okay.
But that inherent sequential nature of RNNs, that remained a huge bottleneck.
So essentially, if you had a long sequence, the RNN would essentially have to read it word by word.
Yeah, exactly.
Which, yeah, that would be really slow.
Very slow.
And I know that you mentioned the concept of attention, and that wasn't brand new.
Yeah, that's right. Attention mechanisms were already around before this paper.
Okay.
And you would find them as a component in some sequence models.
Okay.
Often they were used with RNNs. The basic idea of attention is to allow the model to kind of focus on the most relevant parts of the input when it's processing something.
Okay.
Or generating an output.
All right.
And the distance between those parts, that doesn't really matter. It can focus on what's important regardless of how far apart those elements are.
It kind of sounds like how a human reads.
Yes. It's very much like that.
Like if you're reading a paragraph and there's a reference back to something earlier, you kind of like...
Yeah, you jump back up.
Your
eyes dart back and forth.
And make that connection.
Exactly.
So like in the sentence, the quick brown fox jumps over the lazy dog. To really understand jumps. You probably need to like look back at fox and dog.
Right, exactly. Because they're the actors, right? You've got the fox doing the jumping, the dog being jumped over.
Yeah.
Even though those words aren't right next to jumps, attention would allow the model to make those connections.
I see. And so before this paper, attention was typically used with RNNs.
Yeah, that was the standard approach.
Yeah.
The RNN would still be doing the heavy lifting, handling the sequential processing.
Yeah.
And attention was just kind of there to help it out.
Okay.
Figure out which input elements to pay more attention to at each step.
So what was the big aha moment? What was the revolutionary aspect that led to the transformer?
The authors of this paper, they really wanted to minimize that sequential computation.
Okay.
And really maximize how much of the processing could be done in parallel. And they asked a really important question. Can we ditch the RNNs altogether?
Wow.
Can we just rely on attention to understand and generate sequences?
Okay.
And that was the spark. That led to the transformer.
Were there other attempts at the time to tackle this parallelization problem? Maybe using different types of networks.
Yes, definitely. Convolutional neural networks, or CNNs, were also being explored for sequence modeling.
Okay.
Architectures like extended neural GPU, ByteNet, conv-S2S, these all used convolutions as their main building blocks.
Gotcha.
And that does allow for some parallel computation because you can apply these filters across multiple positions in the input at the same time.
Okay, so if CNNs had some parallel processing capability, what were they lacking compared to the transformer?
The main issue with CNNs was the number of steps it took to capture relationships between distant parts of a sequence.
Okay.
So, for example, with conv-S2S, the number of operations needed to connect two words grew linearly with the distance between them. Mm-hmm. And for ByteNet, it was logarithmic.
Okay.
So if you wanted to understand the connection between two words that were really far apart in a sentence, you still needed a lot of layers to make that happen.
Okay.
It wasn't as direct as it could be.
And so the transformer kind of solves that problem by making that a fixed number of operations.
Yeah, that's the beauty of it. With the transformer, any position in the sequence can directly attend to any other position, no matter how far apart they are, in just one attention layer.
Oh, wow.
So you can imagine how much faster that is.
Okay.
And how much more efficient it is at capturing these long-range dependencies.
Yeah. Yeah, absolutely. Now, I keep hearing the term self-attention thrown around.
Right.
What exactly is self-attention, and how does it differ from the broader concept of attention that we've been discussing?
So self-attention is a specific flavor of attention where you're only looking at relationships within a single sequence.
Okay.
All the queries, keys, and values come from the same input. Mm-hmm. Think of it this way. For each word in a sentence, you're comparing it to all the other words in that same sentence to see how they relate.
Okay.
And based on those relationships, you get a richer representation of each word, taking into account its context. This allows the model to pick up on things like, this pronoun refers to that noun earlier in the sentence, or this verb is modified by that adverb over there.
Okay, that makes sense.
Self-attention itself wasn't brand new. It had already been used successfully in some tasks, like reading comprehension, where you need to understand the relationships between sentences in a paragraph, or text summarization. Mm-hmm. But again, it was usually used alongside RNNs.
Okay.
The aha moment here is that the transformer was the first model to completely ditch the RNNs.
Wow.
And say, we're going all in on self-attention for sequence transduction.
Okay, that was a bold move.
That was a huge risk, but it paid off big time.
Yeah, it sounds like it. Okay, so now we understand kind of the limitations of the previous models. We understand this core idea of attention, especially self-attention. Mm-hmm. So now let's get into the specifics of how the transformer architecture actually works.
Okay, sounds good.
The paper describes this encoder-decoder structure.
Right.
What are these two parts and what do they do?
So, the encoder-decoder structure is very common in a lot of successful sequence transduction models.
Okay.
The encoder's job is to take the input sequence, like our English sentence, and transform it into a sequence of continuous representations.
Okay.
You can think of this as a more compact, information-rich version of the input.
Gotcha.
And then the decoder takes over. Mm-hmm. It uses that encoded representation to generate the output sequence, the French translation of our English sentence.
Okay.
And it does this one element at a time, typically in an autoregressive way.
So that means it's using the words it's already generated to help predict the next word?
Exactly.
Okay, so the transformer follows this encoder-decoder design.
Yes, it does.
But it implements it in a unique way, right? Using those self-attention layers we talked about.
Exactly. Both the encoder and decoder in the transformer are stacks of these self-attention layers interleaved with simple feed-forward networks.
Let's start with the encoder.
Okay.
What does the encoder look like in the transformer?
So the encoder is basically a stack of n identical layers.
Okay.
In the base model they describe in the paper, n is 6.
Okay, 6 layers.
Yeah.
And they're all identical.
Yep. Each of these layers has 2 main sublayers.
Okay.
The first one is our multi-head self-attention mechanism.
We'll get into the multi-head part in a bit.
Yeah, we'll break that down.
Okay.
And then the second sublayer is a position-wise, fully connected feed-forward network.
Right. So 6 identical layers, each with those 2 sublayers. The paper also mentions residual connections and layer normalization.
Right.
What are those for?
So those are really important techniques for training these very deep neural networks effectively.
Okay.
A residual connection basically adds the original input of a sublayer to its output.
Okay.
It's a shortcut.
Okay.
And this helps to address the vanishing gradient problem, which can happen when you have lots of layers. Mm-hmm. It allows gradients to flow more easily during training.
I see.
And then layer normalization, that helps to stabilize the learning process. It normalizes the activations within each layer.
Okay.
And the transformer, they apply these techniques around each of the sublayers. Mm-hmm. So the output of a sublayer ends up being layer norm x plus sublayer x, where x is the original input.
And what about the dimensionality of these representations, like the vectors that represent the words and the information flowing through the network? Is there a standard size for those?
Yes. They make sure that all the sublayers in the model, as well as the initial embedding layers, produce outputs of the same dimension.
Okay.
This is important for the residual connections to work properly.
Okay.
And they call this dimension D model.
Okay.
In the base transformer, D model is set to 512.
Okay, so everything is operating in this 512 dimensional space.
Exactly.
All right, that makes sense. Now, what about the decoder? How is that structured?
The decoder is also a stack of n identical layers, just like the encoder.
Okay.
And it also uses residual connections and layer normalization around each of its sublayers.
Okay, same as the encoder.
Yeah, but there's a key difference. The decoder has an extra sublayer.
Okay.
In addition to the multi-head self-attention and the position-wise feed-forward network.
Okay.
It has a third sublayer that performs multi-head attention over the output of the encoder.
So the decoder is looking at the information that the encoder has extracted from the input sequence.
Exactly.
To help it generate the output.
It's using that encoded representation to guide its predictions.
Okay, the decoder also has its own multi-head self-attention sublayer, right?
Yes, it does.
But there's something about masking in the decoder's self-attention. What's that about?
Right. So the decoder is generating the output sequence one step at a time. Mm-hmm. So we need to prevent it from peeking ahead.
Okay.
We don't want it to see the words that come after the one it's currently trying to predict.
Right. That would be cheating.
Exactly. So they use masking in the decoder's self-attention to ensure that when it's predicting the ith word, it can only attend to the words at positions less than or equal to. It can look at the words it's already generated, but not the ones that come later.
That makes a lot of sense.
This masking, along with the little trick they do with the output embeddings, ensures that the decoder remains autoregressive.
Okay, so it maintains that step-by-step generation while still being able to use parallel attention.
Exactly.
Okay, that's really clever.
Yeah.
Now, I think we've got a pretty good grasp of the encoder and decoder structures. Mm-hmm. Let's get to the heart of the transformer. This attention mechanism.
Okay.
The paper describes this thing called scaled dot product attention. How does that work? What's the basic idea behind it?
So at its core, attention is about taking a query and a set of key value pairs.
Okay.
And then using those to produce an output.
Okay.
It does this by calculating a weighted sum of the values.
Okay.
The weights are determined by how compatible each key is with the query.
So it's like searching for something.
Yes.
Yeah.
It's like using a search engine.
Okay.
You have your search term, which is the query. And then you have all these web pages with their keywords. Those are the keys.
Okay.
And the content of those web pages, that's the values.
I see.
Attention helps you find the most relevant web pages based on your search term.
So how does scale dot product attention actually implement this idea?
So you have three inputs. Queries, which we call Q, keys, which are K, and values, which are V.
Okay.
The queries and keys have a dimension of dk, and the values have a dimension of dv.
Okay.
And for each query, you calculate its dot product with all the keys.
Okay, so you're essentially measuring the similarity between each query and each key.
Yeah, exactly.
Okay.
And then you divide those dot products by the square root of dk.
Why do you need to scale them like that?
So for larger dimensions, those dot products can get really big.
Okay.
And that can lead to very small gradients after you apply the softmax function,
Okay.
which can make training difficult.
Right, so scaling helps with the training process.
Exactly. It keeps those gradients in a healthy range.
So what happens after you scale the dot products?
Then you apply the softmax function.
Okay.
This converts the scores into probabilities, which represent how much weight or importance each value should have relative to the query.
Okay.
And finally, you compute a weighted sum of the values using those softmax probabilities as weights.
Gotcha. So dot product to measure similarity,
yes,
scaling, to help with the gradients, softmax to turn the scores into weights.
Yes.
And then you combine the values based on those weights.
Exactly. And that weighted sum is the output of the attention mechanism.
Now, the paper also talks about additive attention. Why is scaled dot product attention preferred over that?
So in theory, both have similar computational complexity.
Okay.
But in practice, dot product attention is much faster and more efficient in terms of memory usage.
Okay.
And that's because it can heavily utilize matrix multiplication, which is highly optimized in modern hardware and software. Additive attention uses a feed-forward network to calculate the compatibility between the query and key, which can be slower, especially for larger dimensions.
So for the transformers architecture, scaled dot product attention is the better choice.
Yes, especially with the large D model size they use.
Okay. Now, scaled dot product attention is the basic building block, but the actual layers use multi-head attention.
Right.
What's the benefit of having multiple heads?
So instead of just performing one attention operation with the full B-model dimensional vectors, multi-head attention allows the model to look at the relationships from multiple different perspectives. It's like having multiple experts giving their opinions on the same problem.
Gotcha.
Get a more well-rounded understanding.
So how do these multiple heads work?
You essentially create H different heads, where H is a hyperparameter.
Okay.
In the base model, they use H8.
Yeah.
So you take your original queries, keys, and values, and you linearly project them H times each time with a different learned projection matrix. This gives you a different sets of lower dimensional queries, keys, and values.
Okay.
You then perform the scaled dot product attention on each of these sets in parallel.
So you're running 8 separate attention mechanisms at the same time?
Yes, exactly.
Okay.
And each of those produces a DV dimensional output. Then you concatenate all those outputs together and project it one last time to get the final output of the multi-head attention layer.
Okay, so it's like you're gathering insights from these 8 different experts and combining them into a single representation.
Exactly. And this multi-head approach is really important for capturing all the nuances of relationships in the sequence.
Why is that? What's the advantage of having these multiple perspectives?
Imagine you have a single attention head trying to understand a complex sentence.
Okay.
It has to figure out all the relationships between the words, like subject-verb agreement, pronoun references, long-range dependencies, all in one go.
Right.
With multi-head attention, each head can specialize. One head might focus on subject-verb agreement, another on pronoun resolution, another on long-range semantic connections.
I see.
So by combining the outputs of these specialized heads, you get a much richer understanding of the sentence.
Okay, yeah, that makes a lot of sense. And the paper describes 3 different ways that this multi-head attention is used within the transformer, right?
Yeah, that's right.
Could you elaborate on those?
Sure. The first one is called encoder-decoder attention.
Okay.
It's used in the decoder, and it works by taking queries from the previous decoder layer and using the keys and values from the output of the encoder.
Okay.
This allows every position in the decoder to attend over all the positions in the input sequence.
Okay.
So when the decoder is trying to predict the next word in the translation, it can look at the entire input sentence and figure out which parts are most relevant.
Okay, that makes sense. And what about the second application of multi-head attention?
The second one is called self-attention in the encoder. Here, all the queries, keys, and values come from the output of the previous encoder layer.
Okay.
This allows each word in the input sequence to attend to every other word in that same sequence. So the encoder is essentially building a rich representation of each word, taking into account its context within the sentence.
So the encoder is understanding the internal relationships and structure of the input sentence itself.
Exactly.
And the third application.
The third one is also called self-attention, but this time it's in the decoder.
Okay.
And it's similar to the encoder's self-attention, except for one crucial difference. Masking.
Right. The masking we talked about earlier.
Exactly.
Okay.
So in the decoder's self-attention, each position can only attend to the positions that come before it in the output sequence. This ensures the autoregressive property that the model is only using information from the past to predict the future.
So each word in the translation can only be influenced by the words that have already been translated. That makes sense. Okay, so we've covered how multi-head attention is used in these different parts of the transformer, but what else is going on in there? The paper mentions position-wise feed-forward networks. What are those?
Right. So in addition to those attention sublayers, each layer in the transformer also has these position-wise feed-forward networks.
Okay.
And they're position-wise because they're applied to each position in the sequence separately.
Okay.
It's like having a small independent neural network for each word.
Gotcha.
And they consist of 2 linear transformations with a ReLU activation function in between.
So what's the purpose of these feed-forward networks? What do they add to the model?
So the attention mechanisms are great for capturing relationships between words across the sequence, but these feed-forward networks, they allow the model to further process the representation of each word individually based on its context.
So it's like taking the information from the attention mechanism and refining it at each position. Okay, that makes sense. Now, how does the model actually deal with words? Like, how are they converted into something the network can understand? I think the paper talks about embeddings.
Yes, the transformer uses learned embeddings to convert the input and output tokens, which could be words or subword units, into these continuous vector representations.
Okay.
These vectors are d-model dimensional, and they basically capture the meaning of each word in a numerical form.
So it's like each word has its own little point in this 512 dimensional space.
Exactly. And the position of that point reflects the word's meaning.
I see.
And for the final output of the decoder, there's a learn linear transformation, followed by a softmax function. This takes the decoder's output and turns it into a probability distribution over all the possible words in the vocabulary.
So it's like saying, based on everything I've seen, these are the most likely next words in the translation.
Exactly.
Okay. Now, one thing that's been bugging me a little bit is how the transformer deals with the order of words in a sentence.
Right.
It seems like with all this parallel processing, it might lose track of which word comes first, second, and so on.
That's a great observation.
The paper talks about something called positional encoding. What is that?
Yeah, that's a crucial part of the transformer.
Okay.
Because you're right, self-attention doesn't inherently have any sense of order.
Right.
So they introduce these positional encodings to provide the model with information about the position of each word in the sequence.
Okay, so it's like giving each word a unique tag based on its location in the sentence.
Yeah, exactly.
How do they create these positional encodings?
In the paper, they use sine and cosine function of different frequencies.
Okay.
So for each position in the sequence, you generate a vector of values.
Okay.
And the values in this vector are determined by these sine and cosine waves.
Interesting. So why sine and cosine waves?
Well, they have this nice property where they create these oscillating patterns.
Okay.
So you end up with a unique fingerprint for each position in the sequence.
I see.
And the model can use these fingerprints to distinguish between words at different positions.
Even though the attention mechanism itself doesn't inherently know about order.
Exactly.
That's pretty clever.
And the specific frequencies they use for these sine and cosine waves, they're chosen so that the model can easily learn relationships between words at different positions.
Okay.
For example, it can learn that the second word and the fourth word always have a specific positional relationship.
Gotcha. So it's not just about knowing the absolute position of each word, it's also about understanding the relative positions between words.
Exactly.
That's really cool. They also mentioned experimenting with learned positional embeddings, right?
Yes, they did.
Were those less effective than the sine and cosine approach?
Interestingly, they found that the learned embeddings performed almost as well as the sinusoidal ones.
Okay.
But they chose to use the sinusoidal ones in the final model because they thought it might help the model generalize better to longer sequences. Okay, I can see that. Like, if you only train the model on sentences up to a certain length,
right,
it might have trouble dealing with sentences that are longer than that.
Exactly.
But if you use these deterministic sine and cosine functions, you can theoretically calculate the positional encoding for any position, no matter how long the sentence is.
Yeah, that's the idea. So it makes the model more robust to variations in sequence length.
Okay, that makes sense. All right, so we've gone over the main architectural components of the transformer. Now, the paper argues that this self-attention approach is superior to previous methods like RNNs and CNNs. What are the key advantages?
Yeah, they compare self-attention to those other architectures based on 3 main things. Computational complexity per layer, the degree of parallelization, and the path length for information to travel in the network. Okay, let's break those down one by one. What about computational complexity?
So for a sequence of length n and a representation dimension d, a self-attention layer has a complexity of roughly ON2D. A recurrent layer has a complexity of OND2. And a convolutional layer with a kernel size k has a complexity of OKND2.
So self-attention can actually be more efficient than recurrent layers under certain conditions.
Yes, exactly.
Okay.
When the sequence length n is smaller than the representation dimensionality d, self-attention is more efficient.
And that's often the case in natural language processing, right?
Right. Word embeddings tend to be quite high dimensional.
Gotcha. Now, what about parallelization? This is one of the main motivations behind the transformer, right?
Yes. And this is where self-attention really shines.
Okay.
The minimum number of sequential operations you need for a self-attention layer is O1.
Okay, so it can process everything in parallel.
Exactly.
Okay.
In contrast, a recurrent layer needs ON sequential operations.
Because it has to go step by step.
Exactly. Each step depends on the previous one.
Okay.
And a convolutional layer, while it has O1 sequential operations per layer, you need to stack multiple layers to get a larger receptive field.
Right. To be able to look at a wider context.
Exactly. So the information has to travel through more layers, which makes it less parallel.
Okay, so self-attention's ability to process the entire sequence in parallel gives it a big advantage in terms of training speed.
Absolutely.
What about the path length? What does that refer to?
So the path length basically measures how far information has to travel through the network to connect distant parts of the sequence.
Okay.
In a self-attention layer, the maximum path length is O1.
Okay.
Any two words can directly interact with each other in a single layer.
Okay.
In contrast, a recurrent layer has a path length of ON.
Mm-hmm.
The information has to flow sequentially through all the intermediate steps.
Right.
And even with stacked convolutional layers, the path length still grows logarithmically or linearly with the distance.
So self-attention provides a much more direct connection between distant words.
Exactly. It makes it much easier for the model to learn long-range dependencies.
Now, the paper also briefly mentions restricted self-attention. What's that about?
So, for very long sequences, the ON2 complexity of self-attention can become a problem.
Okay.
It might just take too much computation.
Yeah, I can do that.
So one idea they propose is to restrict each position to only attend to a window of size R around it.
Okay.
So instead of looking at the whole sequence, each word only pays attention to its immediate neighbors.
So it's like you're limiting the scope of the attention mechanism.
Exactly.
But wouldn't that make it harder for the model to capture those long-range dependencies we were talking about?
Yes, there's a trade-off.
Okay.
You gain computational efficiency, but you lose some of that ability to model long-range relationships.
I see.